Hi, my name is John Colacelli, and this video is about myosins and how they move along actin. I'm going to use these strings to represent an actin filament, which is made from a chain of actin monomers, two chains of actin monomers that are wrapped around each other. And because actin filaments are polar, I'm indicating here where the positive end of the actin filament is. I'm going to use this boxing glove to represent the myosin head domain. That's the part of the myosin that binds to actin and hydrolyzes ATP in order to move along the actin filament, moving always towards the positive end. We're going to talk about three types of myosin: type 1 myosin, type 2 myosin, and type 5 myosin, and what distinguishes one from the other. Let's start then with type 1 myosin. Type 1 myosin functions as a monomer, and one end of the monomer is connected to lipids in the plasma membrane. The other end of the monomer, the head group, connects to cortical actin, which is a network of actin filaments underneath the plasma membrane. When the type 1 myosin connects to the actin filament and cortical actin and hydrolyzes ATP, what it does is to tug. It moves along the actin filament, again towards the positive end, and this creates a bit of tension, but reinforces the connection between the plasma membrane and the cortical actin. This is important for cells to provide support for the plasma membrane. Okay, we're going to go on now and talk about type 2 myosin, and for that I need to add an additional actin filament, which I'll do right now. Okay, we're back, and we're going to talk about type 2 myosins. We now have two actin filaments, and notice that the two filaments are anti-parallel. That is, the plus end of one filament is in the opposite direction from the plus end of the other filament. Type 2 myosins initially form dimers, and then multiple dimers come together to form an oligomer. So the type 2 myosin that works on actin and the cortical actin network is a series of multiple dimers that come together, and some of the head groups will bind to one actin filament and others to an actin filament that is anti-parallel. When they hydrolyze ATP, they pull then on the two actin filaments but in different directions, and so what we get is sliding along the actin filaments, and this creates tension in the cortical actin. The tension they provide in cortical actin is critical for cells because it provides a force that counteracts the hydrostatic pressure that's coming from inside the cell, pushing outward against the plasma membrane, and also supports the plasma membrane when there are forces pushing in and pinching on the cell from the outside. There's another type of type 2 myosin, and that's the muscle type 2 myosin. So the way that it's different is that it forms very large oligomers, also built up from dimers, but many dimers, and can have hundreds of head groups. Within the structure in muscle that's called the sarcomere, there are then these large filaments of type 2 myosin, and they're surrounded by hundreds of actin filaments, again, anti-parallel to each other. The muscle type 2 myosin then, again, head groups on the oligomers bind to anti-parallel actin filaments and tug, causing a sliding of the filaments, and this is what causes the contraction that we know of as muscle contraction that's taking place in the sarcomeres. Many head groups moving on many actin filaments and taking multiple steps, adding together to give us the type of muscle contraction that we're aware of on a large scale. Okay, we're back, and type 5 myosin also forms a dimer, but this is a different sort of dimer. Now the two head groups are both connecting to the same actin filament. And the type 2 myosin is itself connected to cargo, typically a vesicle that includes proteins and other components. When the type 5 myosin connects then to the actin filament and hydrolyzes ATP, with each cycle of hydrolysis, one head group moves over the other head group. The other head group disconnects and moves over that first head group. What we get then is processive movement along the actin filament towards, again, the plus end. And it's processive because one motor domain is always bound to actin while the other head domain is moving. This allows the cargo and the myosin to remain connected while also moving along the filament. So to review then, we've talked about three types of myosin. Type 1 myosin is a monomer that connects the plasma membrane to the cortical actin network underneath. Type 2 myosin is a dimer and an oligomer of dimers that connects to antiparallel actin filaments in order to create tension, either tension in the cortical actin filament below the plasma membrane, or as we saw for a specialized type of type 2 myosin in muscle cells, to create contraction of muscle. And then finally we talked about type 5 myosin. Type 5 myosin, the dimer that connects to a single actin filament and moves processively, bringing with it a cargo to get from one end of the filament to the other end of the